All right, thank you. Thank you for the introduction. And I realized when I get asked to send in a quick summary of I should make it shorter than my talk itself. Just, but yeah, so today I want to talk a bit about X-ray reconstruction. And so last year I was standing exactly here talking about our software where we can reconstruct directly into a tetrahedral mesh basis our X-ray imaging rather than have voxels. So today I want to talk a bit about tetrahedral basis, but as you can see or not see, the mesh, which was in the title, I kind of made it slightly less prominent, because I'm going to talk more general about how to represent the image that we're reconstructing in an X-ray tomography problem, and what are the different bases that we have and what can we do with them afterwards. All right, let's see if oh yeah, it's working already. It's slower than me. All right, so one of the motivations for this work is that often in X-ray reconstruction, we do have prior information about what we're actually reconstructing. And so especially in kind of manufactured components, we often have a good idea of the shapes involved that we're looking for in the object. And we always want to use as much information in the reconstruction as we can to get away with using as little data as possible. And in this talk, the focus will be, how do we use this type of prior information, but also how do we use what I would call adaptive basis. So not a fixed base. So often when we reconstruct an image, we fix the image basis. And I'll say what I mean by a basis, but we break everything in voxel. We say how many voxels we want to reconstruct into the voxels, and we are done. Now that is not necessarily the best way of going about it. Once we reconstructed our image a bit, we might ask our question: is the basis I've chosen to represent my image actually the basis that's good for my image, as far as I know what the image looks like so far from my measurements? All right, so now I don't want to go through all the next few slides. I want to skip a few slides, but so I'm talking about image representations here and image basis. So mathematics and kind of functional analysis of basis is just a representation of a function. So we think of our image, whether in 2D or 3D, as a continuous function of, say, gray values. And we kind of represent that by breaking it into simpler functions. So we are used to voxel basis, where we kind of break everything into blocks. That's one way of representing the image. Last year, I talked about tetrahedral. We kind of break everything into tetrahedral and represent the gray level in each spatial location as a combination of these tetrahedra, and each tetrahedra has a different gray level. But there are loads of other bases we could choose. They don't have to be mutually exclusive. So, voxels, there's one voxel stops and the next voxel starts. There can all be overlapping these bases. But today I kind of stick with nicely bases that are mutually exclusive. And yeah, don't want to go into too much detail. Now, often when we have an object that we want to represent, an X-ray, we're looking at attenuation, and the attenuation, we need a good resolution where edges are, and we might need good resolutions at the image where there's something happening, but we might often get away with less high resolution in areas where either the attenuation is uniform or where we're not interested in what we're looking at. And that, so today I'm going to talk about different ways of achieving that. And also different ways of different ways of representing this variation in the basis over space. So what basis can we choose, but also how do we choose them? So there are kind of two questions: what basis to choose, and how do we, once we've chosen the type of basis, how do we then adapt that basis for what we want to do? If you get the phone out, not because I'm taking a phone call, just to keep an eye on the time. All right, so. And today I'm going to talk, let's call it, and I know it might not be a universally used term, but so I talk about superpixels, and I come to, or voxels if you want. I talk about variable size voxels, and I have a distinction between those. And then I talk about tetrahedral meshes. So these are kind of the basis functions that we use. And so here's kind of an example of what one might think of as a supervoxel. So obviously, this is a very simple image. That's why we, mathematicians love that, and computer scientists. It's very simple. It has a couple of gray levels, and if we know, the different areas, we can kind of use a basis where each area has its own kind of single function, and we just represent each instead of having voxels, we just have these big clusters of voxels. So here the underlying is still a voxel, but we grouped all these voxels together. And each part of our object that we know exists, we just give it one gray value. It's a group of voxels, but all these voxels share the same gray value. And I called it super voxels, but whatever we want to call it. So, often when we have an object, we scan an object, for example, we can get whether we have CAD data, we can get a good estimate of, where in our image are different areas. So we can just get a very simple basis. And here we just, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 areas. So we only need to estimate 10 gray values. Assume it's to the background to be 0. So here we have 10, 10 numbers that we need to estimate because we know if you know the areas. So that makes our tomographic reconstruction problem much easier. Obviously, we lose, if there's more detail than these uniform areas, we lose that detail. All right, so talking about voxel-based bases, the other thing that we can do is instead of defining bases regions, kind of prefixing regions, we can have a basis where we still have voxels, but the voxels are different sizes. So we can start with a big voxel, which we can break then in 3D, we break it into 8 smaller voxels and so on. And, so if we take, again, our simple image, and here in the middle, I just show the voxel basis, just assigned random colors to each voxel, just to show you roughly the change in variation. So we have kind of big voxels, and all these voxels, pixels actually square. Just a random assignment here gave me colors that look very similar. So, they're all square voxels, but depending on where we need higher resolution at edges, we just have more of them, of finer, smaller voxels. So we can talk about a representation of our image within these voxels, and the image on the right is the same as the image on the left, but using these voxels. You don't see any difference between that one and that one, just because this set of voxels, there's 5,000 different voxels in here, all of different sizes, and they just allow me to get exactly the same resolution as I have in this original image with many other voxels I had in the area. It's 256 by 256. Just on there, it's 65,000 pixels of voxels. So if I have objects that are nicely uniform with edges, having a variable size basis is really useful in terms of significantly reducing the numbers of voxels that I need to estimate in my reconstruction problem. All right, so these are kind of still voxel based, or variable size voxels, or kind of groups of voxels if you want. The third one, and which is kind of what I talked about last time, is we can directly reconstruct also in kind of more general basis functions. So typical mesh representation is just, again, a simple shape. We can project, get sinograms of that, and then get a reconstruction directly into a mesh type basis. Should have really plotted in gray scale. So we have a background gray level and the foreground gray level. Now the reconstruction mesh here is different from the mesh I started with, because I don't know necessarily what exactly the shape is, and that's one of the problems I have with all of these things. I don't know exactly where my object is, and I don't know exactly. I might have a good idea of roughly what the shape is, but it's never exact what I'm looking for. And you see, obviously with this type of representation, because even though I simulated the data from this mesh, if I have a slightly different mesh, I don't get a very nice edge, obviously, because the true edge kind of lies in between somewhere here, and you at least get these different colored cells. All right, so now the next kind of part of the talk, having these different types of bases, and I want to see, first of all, how can we use these in a reconstruction? How, what are the different options there are for us in terms of utilizing them to get a good reconstruction? And the focus here is on adaptation. So we don't fix the basis at the beginning, or we might fix it at the beginning, but that's probably not the best way of going about it. We kind of want to adapt the basis somehow. All right, so let's start just with using these kind of masks, and this is actually kind of just a very simple object, just kind of one face really. And if we just have very few projections of our image, we get standard limited angle or limited number of projection type artifacts. So standard filtered back projection doesn't get us very far. And here I just applied the mask. So even if we know where our object is, how do we best utilize that information? Just cutting out using the mask as a cookie cutter at the end and just cutting out after filtered back projection doesn't really get us anywhere, because we still have the same artifacts in the image as we had before. We just cut out the shape, so just set everything to black in the background. So that's where iterative algorithms come in, because iterative algorithms can use this type of information much more efficiently. And I guess I'm showing the filtered back projection reconstruction again on the right, but we can use an iterative reconstruction. And I don't want to go into the details, but the iterative reconstruction I'm using here is just a gradient descent algorithm with a prox operator that kind of projects onto whatever basis I'm going to talk about. And here I'm just having what project onto, basically just cuts out it just applies the mask basically to the image. You do that iteratively. And we say, we don't have quite as many artifacts. We have different types of artifacts that seem to be creeping in if you use this mask and run it for too many iterations. So there are instabilities, and we have, this is a projection with, I think it was just 18 projections. So it's quite a challenging problem to solve. And even, so just using the fact that we know where the shape is. And here we don't make any assumptions of that. We assume a uniform gray level in the background. So this is just cutting out the object. So this is actually not a super voxel in that sense, because, if we had a super voxels, we just would obviously get that shape back with one gray value, which would then look like the original, but that's a bit contrived. So here we just use the mask to cut out the image, and the message here really is, mask gets you that far, but there are issues with just using masks. So if you just know the shape of the object, you just use that in your iterative reconstruction. For example, if your mask is slightly shifted to where the real object is, you tend to get kind of artifacts around the edges of your object. And you see there's quite a lot of variation in the gray value that we're looking at here. So if you have a mask, you need to make sure it's either larger than the object you're looking for, or it at least includes, it is in the right location. So that's obviously, in a real application, that can be challenging. However, here's one thing that you can do, for example. Here is a mask that I generated from my projections themselves. Let's call it the convex hull of my object. So I have my object and I take my X-ray projections, and then I threshold the X-ray projections into, there is an object or there's background. And then I kind of back project these thresholded projections, and I'll use a logical AND operation if you want, rather than adding your back projection as you would do in a filtered back projection operator. And that kind of creates a the convex hull of your object. Because all the X-ray beams that go past it, you know where they are. And by taking account of all these X-ray beams that go past your object just about, and those that are just inside the object, you kind of get the convex hull. Now, this approach doesn't use any prior information, it just uses the projections, and it's kind of obviously insensitive to your object location. And we get reconstructions that, so this one is the one with the full mask, where the full mask also included, cut out these black bits here. Obviously, the convex hull doesn't include that's why this object looks like that, because I don't want the things inside that will only cut out. But yeah, if I use this mask for the reconstruction, again, I get some better reconstruction than I got, without the mask. All right, so that's kind of how far you can go with masks if you want. Obviously, you can take all different levels, and we couldn't make it all uniform nicely inside, and it would look very nice, but that's slightly unrealistic. So obviously mask, if the mask fits well, you do constrain your problem to some extent and you get a bit of benefit. You can't really drop the projections quite as far as I did here. So 18 projections probably would have needed more like 300 projections here. So it's, more than 10 times reduction in kind of the measurements that we would have needed to get a full reconstruction. And by using the mask is roughly half the size of the image here in this example. So my constraint only reduces my problem size by half, whilst I reduced the amount of data by a tenth. That's kind of a rough estimate of, what are we trying to achieve and is it sensible? But we've seen, if the mask doesn't quite fit, we get artifacts from the mask itself, from, because we're now cutting back stuff out of the object when we're reconstructing it. The larger the mass in the object relative to your number of measurements, the less well it works. All right, so let's look at the second kind of type of thing that we can do. So this variable size basis, again, this variable size basis we can use in different ways, and there, I think there are some interesting things that we can do. So how do we, so obviously we could use again, like we did on the previous picture, we could use that mask that's kind of based on our knowledge of our ground state or true state, but we kind of, if you get this information from cut data, we know where the edges are. You can, generate a mask with a variable density. Mask kind of basis with a variable density, and you can use that in your reconstruction. But again, you have the same problems if things shift. So it's more interesting to look at adapting your basis iteratively. So, and the first way of you could, in doing your reconstruction, adapt your basis is, so again, we're using the same data, and basically I start with a very low number of uniform sized voxels, and then I just look at kind of an error measure, which voxel do I need to break up to kind of get a better basis. And then I'm, slowly increase the number of voxels by breaking those that give me a large reconstruction error, and I get a better and better kind of representation of the image, and I get much sharper. You typically break down these voxels at edges, and that works to some extent. So kind of this adaptation where you start with a low resolution and then doing your reconstruction, iteratively refine the basis based on the reconstruction. So that, again, there's no prior information in this. Now that's one way of doing it, but I don't think it's the best way. It's probably better. Oh yeah, let's not talk about that. So I think it's a better approach where we use where we do some reconstructions, and then we find, for this current step at the reconstruction, we find the best variable basis that fits my current image. So, we do the reconstruction actually here, in all the computations with these variable bases in terms of voxels are still done in the high resolution basis. But then after so many, after each iteration, we then find the best variable size basis to describe what I have. And then we use that to go into the next iteration. So here again, comparing what we have here with kind of the similar image that we had here. This one actually, yeah, somehow we've lost the. Oh, this, I think there's a slightly different example, so it's not easy to constrain. This one was just one gray level. Was obviously here we have all the different gray levels in this basis. It's slightly different to compare, but this tends to work better. So instead of slowly breaking up the basis, as you're going along and kind of refining, because any errors you make early on, you keep on having further down the line. But if each iteration you ask, I have this approximation of my image, what is the best variable density basis to take, seems to work better. All right, so that seems to be kind of, if you want to work with these types of bases, using kind of an iterative algorithm where you break these your bases into the best basis, seems to work well. Actually, what I haven't said on this image, this is actually the reconstruction with just using this variable size basis. These ones are also added some additional smoothness through total variation type regularization. So just having variable basis doesn't because sometimes you get very small approximations, so small errors. So having some smoothness introduced through total variation does help. All right, so with these kind of variable size voxel type representations, that's probably the best way. So the question now is, can you do something similar with tetrahedral type basis representations? And what do you do there? Because tetrahedral, if you could start with a nice uniform tetrahedral mesh, and then each tetrahedral you break into 4 tetrahedra or 3 tetrahedra or whatever you want to slice them, and then you have kind of this tree type representation. That's one way of doing it. It's not very useful, I think. So with tetrahedral, you probably want to do something slightly different. So with tetrahedral, the first thing you could do is you start with some representation, and then you find a refinement of that mesh. So you can refine it either by deciding, oh, these tetrahedra I want to break into 3 or 4. So you fix tetrahedra and you break them, or you just completely remesh everything, but you remesh it so that you have a different density in areas where you need more tetrahedra. So where we have edges and things. And that's really the better approach, I think, now than keeping the fixed tetrahedra where you then break down a certain tetrahedra. It's probably better just to remesh completely the whole volume, and then continue your iterations. All right, and yeah, there's kind of an example of what you get with you start with a rough approximation. So there you should have a kind of square type hole in the middle, and then a round outer object, and you kind of get better and better reconstruction. So it's not quite as good as it could. All right, now the last thing I want to talk about, that's one way of working. The other working with these a general tetrahedral type basis function. So we can remesh or break up tetrahedra. But I think another very interesting thing is, especially if we're talking about objects with kind of defined boundaries, because one of the big problems is you have these tetrahedral mesh, but they don't align necessarily with the boundary that you have. So the other thing how you can adapt your mesh is you just move nodes in your tetrahedral mesh. So during your iteration, you say, oh, there's a boundary here probably somewhere because I've got some error here. It doesn't quite fit my model, my basis doesn't quite fit my observations. And then you ask, at these points where I need to have this error, maybe I just move tetrahedral points around a bit. And so this example just shows that. So I basically just have a square block, and the original object is kind of slightly larger than the mesh I have. And then if you basically adapt your basis by calculating the derivative of each mesh point with respect to your reconstruction error, we get better and better edge representations. You see, slowly that's our initial start, and the edges of the tetrahedral mesh lines its edges better and better with our object. All right, that's kind of where I'm running out of time, I think. So there are different ways of using bases that are not uniform. So the oct, I call them octree, because when you're breaking your voxels into 8, it gives you a nice octree representation. It has advantages computationally. Tetrahedral meshes are more general, but computationally more expensive. And both of them kind of allow you to do slightly different things and how to deal with them. And I think I'll leave it at that before I get dragged out of the stage. Any questions?